All right. Welcome to today's program on forensic toxicology, methods used, and common errors. The idea for this program came from questions that I was getting from a lot of district court attorneys about drug screening tests. A lot of attorneys ask me about the tests that they see in their DSS cases, probation cases, criminal cases, and other types of cases. And so we wanted to get you some more information about what those tests are and how they work. We know that the tests that you usually ask me about are urine dip tests, but there's other types of samples that are also tested. So we wanted to get you more information about the reliability of those tests and the errors that can be associated with the tests. A lot of times attorneys ask me about test results that seem contradictory, like they might get one result from urine testing, a different result from hair, or the results might be different from what their client is reporting to them. So we wanted to address some of those issues with you today. So we have two toxicologists who have generously agreed to be with us today. I really appreciate all the time that they've put into preparing the program and presenting it today. The real take-home message from this program is that the urine dip tests that are often presented in court are not as reliable as the confirmatory tests that can be performed in the laboratory. And you should consider that in considering whether to challenge the results of these tests. So Dr. Evans and Dr. DeCall will help us to understand how these tests work, what they do, what they can't do, and how to do that. In order to do that, they're going to explain to us how drugs behave in the body, what different types of samples can be tested, and the different methods for testing them. So tomorrow, Dr. Kieran DeCall will be presenting about the toxicology test that can be performed in a laboratory. He has a PhD in human toxicology and is a diplomate of the American Board of Toxicology. He works part-time as a lab director and a consultant for clinical and forensic toxicology labs. So he's with us today, but the bulk of his presentation will take place tomorrow. And today we'll be hearing from Dr. Andrew Evans about the behavior of drugs in the body and about field drug testing. So Dr. Evans has a doctorate degree in pharmacology and he's board certified in toxicology. He has 25 years of experience covering a broad range of areas within pharmacology and toxicology. He has 10 years experience conducting research, 8 years of experience working on legal cases, interpreting drug use, drug-induced impairment, and drug-induced cause of death, as well as providing drug testing services. He's worked on a broad range of case types, including murder and assault cases, cause of death, DWI, retrograde extrapolation, probation violation, post-conviction, personal injury, child custody, medical malpractice, and employment drug testing. He's been qualified as an expert to testify in North Carolina, Texas, Maryland, and Michigan. He conducts research on standardized field sobriety tests and DRE evaluations, sources of mouth alcohol, false positive testing from CBD use, and the source of the alcohol breath smell. And he's also working on developing a new drug detection device. His previous research includes developing an immunotherapy treatment for cancer that cures mice of lymphoma and breast cancer, and developing a new technique for detecting chromosomal damage. He's as contract toxicologist for 15 years with 5 federal agencies, as well as with the Center for Disease Control and Prevention and the Environmental Protection Agency. I don't know where he finds it, but in his spare time, he volunteers with the Cary Community Emergency Response Team, where he's received training from the Raleigh Fire Department in hazardous materials response up to the level of hazmat technician. And he's taught classes on responses to terrorist attacks and hazmat response. He also volunteers with the Cary Citizens Assisting Police, where he has provided support for a DWI checkpoint and assisted in testing bomb detecting dogs for the Transportation Security Administration. So I will now turn the program over to Dr. Evans. If you'd like to start sharing your slide. And again, welcome everybody, and thank you so much for being on the program today.
Okay. Can everybody see this slide? It should say forensic toxicology at the top.
I can see it. I am seeing like your next slide as a preview as well.
Oh, really? Okay.
If you have two screens, you may want to try sharing the screen instead.
Okay. Is that better? Is that just the slide now?
There, now it's just the slide.
Okay.
Great.
Okay, now I can see what I'm doing. Okay, there we go. Sorry. All right, everything's set now. So my name is Dr. Andy Evans, and we are going to talk about forensic toxicology for child custody, DSS, and probation violation cases. And Ms. Olson did pronounce my name correctly. It is spelled with a W, but it is pronounced Evans. It's because it comes from a German origin where W's and V's are swapped. So almost nobody pronounces it right, but it doesn't bother me if that happens. This is a class through IDS, but if in the near future I'm going to be hosting some other classes, maybe some mini classes that are probably about 10 minutes long. If you contact me through my email or through alignable.com, you can, I'll be sending out information about those classes as well. So the main toxicology concern with these types of cases, child custody, probation, is really looking at whether or not a person consumed a drug. It's really a yes or no question, and there's not really much of a concern about how much drug was consumed or whether or not the person was impaired from that drug. So we're going to look at answering some questions with this class. First off, where do you look for drugs? What drugs and metabolites are you going to look for? How are you going to look for these drugs? And then how to interpret the results. So to start off, hopefully there's not too many groans. We're going to do just a little bit of chemistry to help you better understand what I'm talking about today, as well as what Dr. DeCall is going to talk about tomorrow. So quickly, atoms are made up of three primary particles: protons, which have a positive electrical charge, and a high mass; electrons, which have a negative electrical charge, but very little mass; and neutrons that have no charge, but high mass. And why do I keep talking about charge and mass? Because there are two forces that control the behavior of different atoms. So with mass, we have an effect that's very similar to gravity. More mass of a particle, the more gravity it's going to have. And then electrical charge, we'll talk about in just a second. So these two forces are dictated by electrical charge. This is a lot similar to magnets. So here, hopefully you can see this in the little video. If we consider this a positive pole of a magnet and this a negative pole of the magnet, you can see that the opposite poles or opposite electrical charges are attracted to each other. Now, if you turn this around and say these are both positive electrical charges, if I hold this very gently, move them together, you'll see that they are trying to avoid each other. And I'm not moving the red magnet at all. It's just doing that through the electrical or magnetic repulsion. So the point is there that if you have the same charge on a particle, they are going to repel each other. If you have opposite charges, they're going to attract each other. And that's pretty much a way of neutralizing that electrical charge. So if you have a positive charge and a negative charge, they want to combine together to neutralize it so that there is no charge. This is pretty much a fundamental idea in science and nature where things just try to neutralize each other. Then you have gravity, where larger molecules or particles like the neutron and the proton will fall in towards each other because of their gravitational attraction. And it's not really gravity, but just for illustrative purposes, we're going to call it gravity. With an electron, it has such very little mass that the gravitational pull between either protons or neutrons to the electron is pretty small. And if we consider the effects of both of these forces together, the gravitational force is much stronger than the electrical force. That's not to say that the electrical force is weak, but the gravitational force is stronger than the electrical force. So what does this all do? So if we consider the particles that have high mass, the protons and the neutrons, gravity is going to cause them to clump together and form the nucleus of an atom. Now, you may say, we were just talking about electrical charges, so why is it that the protons that are all positively charged are all going to group close together in the nucleus? And again, what I said is gravity is stronger than the electrical charge force, so it can overcome the repulsion of the positive charges of the protons. So now we're going to throw in the mix the electron, which has very little mass, but it has that negative charge to it. So a good way to think about this is kind of like planets orbiting the sun. So if you have we'll say a comet flying through space and it gets near the sun, it is going to get attracted to the sun by the gravitational force, which is going to bring it down. But because that comet is moving so fast, instead of crashing into the sun, it's going to form an orbit around the sun, where it's always kind of falling towards it, but moving so fast that it never actually reaches the center. So that keeps the electrons away from the nucleus, their speed moving around, as well as the negative charges of its neighboring electrons. So as the electrons start to clump around the nucleus, they start to repel each other and push each other further out away from the nucleus. So, as I said, nature tries to neutralize everything. So you have these positively charged protons that are then going to be neutralized by the same number of negatively charged electrons. So you're going to have, in this atom, this is a carbon, you're going to have 6 protons, and that is going to be neutralized by 6 electrons. So there's no charge, and we're going to call that an atom. Say we lose an electron, now we're going to have 6 protons, but only 5 electrons. And that's going to give the entire atom an overall positive charge. And that we then call an ion. So this would be a carbon ion. So how could ionization work? So if you were to take a high-speed electron and shoot it at this carbon atom, what's going to happen is the 2 electrons are going to collide and then knock out of orbit the 1 electron that was part of the carbon atom. So what you get left with is the missing electron, only 5 electrons to your 6 protons, leaving you a positive charge of 1, which we're going to say is a full charge because you've lost an entire electron. And that'll make sense in just a second. So now we're going to look at chemical bonds and how electrons distribute between the chemical bonds will cause different properties in those chemicals. So here we've got 2 carbon atoms. Again, we've got the 6 electrons on this atom, 6 electrons on that atom. 2 of these electrons are going to be shared so that you get the atom on the right will have the electron on top about 50% of the time, and then it'll pass it over to the atom on the left, and the opposite will happen for the electron on the bottom. So they're constantly switching electrons back and forth in a sharing type of cooperation. If we look at the periodic table, this tells us lots of things about chemistry. But the important thing for today is it shows a way of figuring out the electronegativity of an atom. And what electronegativity is basically the ability of an atom to grab and hold on to an electron. So if we look at the atoms over on the right of the periodic table, those atoms will have very strong electronegativity. So they're going to grab onto electrons and hold on, and they're not going to let go. Whereas the atoms over on the left have very little electronegativity. They're very weak, and they can easily let go of their electrons. So we were talking about 2 carbon atoms binding together. So here we've got the carbon atom, which is about in the middle of the range of electronegativity. And since they're both the same atom, both carbons, they're going to have the same level of electronegativity. So they both have a fairly strong pull on electrons. So if we look at this little figure, each C stands for carbon, and this line between them represents the bond, the sharing of those electrons. You see that the red shading represents the distribution of those electrons between the 2 carbons. And because the electronegativity of carbon is the same for either carbon, the distribution of the electrons is pretty much even. So the atom on the right will share the electron about 50% of the time. The atom on the left will share it about 50% of the time as well. So this type of bond is causing an equal distribution of electrons is called a nonpolar bond. And we'll contrast that in just a second with a polar bond. So here we have carbon binding to oxygen. Again, we have the 2 electrons being shared. But the difference is oxygen is further on the right on the periodic table. So it has a very strong electronegativity. So it's really going to pull on the electrons in that bond. compared to carbon, which is strong, but it's not very strong. Not nearly as strong as oxygen. So what happens is the distribution of electrons shown in red here now favors the oxygen. So we symbolize that with a Greek delta sign, saying that this is a partial negative charge. So it's not the same as the oxygen stealing that electron and keeping it for itself, where it would have a full electron charge. It's just that maybe the oxygen holds onto that electron 80% of the time, and the carbon only holds onto it 20%, so that the oxygen has a partial negative charge. And then conversely, the carbon holds onto the electron less, so it has a partial positive charge. So similar to the carbon and oxygen, we've got water, which is made up of 2 hydrogens binding to 1 oxygen. And we have this oxygen with a high electronegativity. It's got the super strong electron grabber. Hydrogen, all the way on the left, has very low electronegativity, represented by this weakling person who cannot hold on to electrons very well. So you've got the ability of the oxygen to really grab onto these electrons. The hydrogens having a really hard time keeping onto their grip to the electrons. So you get a double positive charge on the hydrogens and a single negative charge on the oxygen. So what this does is this difference in charge means that the water molecule is polar, just like a magnet with a north and south pole. The electrical charges can be treated just the same. You've got negative charge on one end and a positive charge on the other. So we call that a polar molecule because it's similar to a magnet. So what happens when you have lots of water molecules together? You've got these positively charged hydrogens attracted to the negatively charged oxygen. So the water molecules are going to line up with their hydrogens facing each other's oxygens, and that gives the water some cohesive strength. And you can see this if you fill a glass with water and you fill it right to the top and then add just a little bit more, you'll see that instead of the water spilling over the edge of the cup, that the water will kind of bubble up for a little bit before it starts to spill over. And it's able to bubble up because of the surface tension of that water caused by the attraction of all the different water molecules to each other. So basically, any molecules that are polar, that have these electrical charges, will be attracted to water and will dissolve in water. Now, if we contrast this with a hydrocarbon, this is created by just carbon and hydrogen. You do have a difference in electronegativity between the carbon and the hydrogen. But as you can see, these hydrogens are evenly distributed throughout the molecule. So if we look at the electron distribution, we can see that this molecule isn't polar and that you don't have a difference in electrical charge over the entire molecule because they are evenly distributed throughout that molecule. So this type of chemical is called nonpolar. There is no electrical difference throughout from one end of the molecule to the other. So if you were to take a hydrocarbon and put it in water, since the hydrocarbon isn't polar and doesn't have an overall positive or negative component to it, it doesn't interact with the water. That only likes to interact with things that are polar or charged. It likes that electrical charge because the water molecule is so attracted to itself. What it will do then is form a structure around the hydrocarbon molecule, kind of like a cage, where it doesn't want to touch the hydrocarbon. It wants to keep its distance. We don't really interact with you, but we interact with each other really hard. So because of that interaction of water to itself, it will form this cage around the hydrocarbon. The problem with that is, as I said before, nature likes to neutralize everything. And part of that is also a force called entropy, where it wants everything to just be evenly distributed throughout the universe. So when you start to form these cage structures with the water around the hydrocarbon, it puts stress on the water. The water doesn't like to be that way. It wants to be more random. And forcing it to form this cage really doesn't make the water happy. So what happens now if we're adding here 4 hydrocarbons into this water? So each one is going to be surrounded by its own cage. So there's now 4 water cages around these molecules. So the water is really upset. It doesn't like it. It wants to be random. So this is a good time for our first question, which is, how can we reduce the stress on the water? If you've got 4 different hydrocarbon molecules in the water, forcing the water to form cages around each one, how can the water reduce the stress and get to a more stable form? So is there can anybody answer that on chat? Just type that into the chat box. How would you reduce the stress in the water with the 4 hydrocarbons to make the water more relaxed?
So we've got one answer, heat.
Not exactly. So what happens is, let's see if I can switch my slide. So what happens is all of the hydrocarbons then clump together so that there's only one cage of water around it. So yes, this cage is bigger, but because it's all condensed into one, the surface area of that cage is smaller compared to having 4 different cages. So that's when you see, if you drop water, a drop of oil into water, they don't mix, because in order to reduce the stress on the water and reduce the number of cages, all that oil clumps together and separates out from the water. So we have another molecule, which is a little bit more complicated now. This is called a fatty acid. And it's composed of a hydrocarbon chain, which is nonpolar and is termed a fat, and a polar acid portion, which thus gives it the fatty acid name. The acid portion has 2 oxygens in it combined to the carbon. So those oxygens are pulling on those electrons from that carbon. And that poor little carbon in the middle is turning very positive, while the oxygens are turning very negative. So this makes the acid portion of this molecule very able to interact with water, and makes it very water soluble. But the fatty component is not water soluble. So we can represent this another way with just a ball and a stick. The ball is the polar water-loving, water-soluble portion, and the stick is the non-polar fatty portion. So if you were to put many of these fatty acids in water, what do you think would happen? They wouldn't just, because they have both this water-soluble head and an insoluble tail. So to, again, minimize the stress in the water, it's going to try to keep the fat region, the non-polar region that is not soluble in water, away from the water. So all of those hydrocarbon tails are going to form a little core inside the ball that is surrounded by the hydrophobic acid portion. And this is also known as a micelle in science, but you probably know it as soap. So basically, this is just a clump of soap molecules. And the way it works is water is a great solvent for any ionic or polar chemical, anything that has a electrical charge in the molecule. Water will grab it, it'll dissolve it. You can rinse your hands off, and the water will just take it away, and your hands will be clean. But not all dirt is that way. Some of it is non-polar, like greases and fats. So you're adding a soap because here you've got the water-soluble portion and then the fatty portion in the middle, and that is able to take an oily dirt, put it inside the core of the soap, and then because it has this water-soluble portion, that dirt will then get washed away when you rinse off your hands. So that's basically how soap works. And we actually have soap in our body, and we'll talk about how that's used to move drugs around. So if you keep adding fatty acids, you can get, under certain conditions, not just this micelle ball, but you can get a planar film where the center is filled with the fat component surrounded by the water-soluble acid component. And where this comes in is if you have these sheets of fat and they form a bubble connecting to each other on all sides, this is actually what forms the outside of a cell, or the cell membrane. So within this fatty bubble, you've got all the different components that make up a cell. So anything that goes into the cell has to be able to cross this fatty layer, and anything that comes out of the cell also has to be able to cross the fatty layer. So if we step back and start looking at a tissue level, here we have the inside of the intestine, which is mostly water, and that is lined with a bunch of cells forming the wall of the intestine. Right next to the intestine is another line of cells, and that forms the outside wall of blood vessels. So you have blood in the middle of your blood vessel and water inside the intestine. And over here on the other side, somewhere else down in the body, we have cells lining other tissue and a watery environment inside that tissue. So if you have a drug that's in the intestine, it is not charged, it has no electrical charge, it's not polar. It's able to go into the fatty cell membranes that are lining the tissue, both the intestine and the blood vessel. Compare that to a drug with a positive charge or a solid electrical charge or a very high polar charge. And so you see that the drugs without the charge are able to get through that fatty layer and into the blood, whereas those polar or charged drugs have a much harder time. And then similarly, once it gets into the blood, it then has to get into tissue. And for the same reason, the non-polar, non-charged drug is able to get through the tissue better than a drug with a lot of polarity or electrical charge. So we'll pause for just a second if anybody has any questions on what we've covered so far. So basically we went from subatomic particles that make up an atom to atoms to multiple atoms and molecules to cells and now onto tissue, and how electrical charges affect each of those levels of chemistry and biology. Okay, I do not see a question, so we'll move on. So now we're going to go and answer the question, where do you look for drugs? So we've kind of set up just the basics of chemistry, and now we want to know where do you find drugs that people consume? So we're going to look into pharmacokinetics. And this is the science of how drugs move throughout the body. And it's composed of 4 different major components: the absorption, which is basically just how does the drug get into the body, and then distribution, where does the drug go once it's inside the body. And by inside the body, we're generally talking about inside the blood, and then in distribution, it is going to other places. And how elimination, which is how does the drug leave the body. And then when the drug is in the body, it can get changed, chemically changed to different chemicals, and that is termed metabolism. So here we're going to look at the blood concentration of a drug on the y-axis in this graph over time. So a person at time 0 has no drug in their body. Then they take a drug, and the concentration of drug in their blood starts to increase, and then it starts to plateau off and will start to come down and decrease over time. So the increase in drug concentration in the blood is called the absorptive phase. This is where the drug is then first getting into the body. This is followed by the plateau, which is called the distribution phase, where the drug is then spreading to other tissues throughout the body, followed by the decrease in drug concentration, called the elimination or metabolism phase. So we'll talk about absorption very quickly. So the main routes of absorption would be through the mouth, through the gastrointestinal tract. We've got 3 different tissue to consider when you take a drug as a pill. You've got the stomach, where the pill is going to go and then sit for a little bit. If we're looking at the tissue over on the right, here we've got the inside of the stomach, which is mostly water, the blood on the other side, 1 layer of cells surrounding the blood, and multiple layers of cells surrounding the stomach. The stomach is actually quite thick, and in addition to the cell layer, it also has a mucousy film that is protecting the stomach from the acids that are produced in the inside the stomach. So a drug then has multiple layers of tissue to go through to get into the blood, plus that mucousy film, and so drugs do not get in through the stomach very easily. If we look at the small intestine, the pill then leaves the stomach, goes into the small intestine. Here we don't have that mucus film on the tissues as much as the stomach, and the tissue is much thinner. Here we've got only 1 or 2 cells keeping, lining the small intestine. So the resistance of that drug to get into the blood is a whole lot lower. So drugs that can sit in the stomach for a while don't get absorbed very fast as when they move into the small intestine. And that can happen if someone were to eat food while they're taking a drug. The act of eating food and putting food into the stomach will close the valve between the stomach and the small intestine. And so the food as well as the drug will sit in the stomach for a little while until digestion is complete. And then the valve opens and the food and the drug get into the small intestine. So this is why you have a much stronger effect of alcohol when you drink alcohol on an empty stomach versus if you were to drink alcohol while you're eating food. Because the alcohol is going to get into the blood better in the small intestine than the stomach. And the food will cause a delay where the alcohol sits in the stomach for a while. Now you can go in the reverse direction and absorb drugs through the colon and rectum. And similar to the small intestine, there is no mucus film in the colon and rectum, but the tissue of the colon and rectum is thicker than you would see in the small intestine. So drug absorption through the colon and the rectum is going to be slower than the small intestine, but much faster than the stomach. This isn't a very common way for people to use drugs, but some people will try to consume alcohol through the rectum because it bypasses the stomach, avoiding the irritant effect of alcohol on the stomach so that a person doesn't get sick and throw up as easily. And by doing that, your body wants to make you throw up if you're drinking too much alcohol. It's kind of like a safety measure. And if you bypass that by taking alcohol through the rectum, it makes it easier to have an overdose. Some drugs can be snorted through the nose, and that tissue is similar to the small intestine. There's no mucousy film and a very small layer of tissue to get into the blood. So drugs get into the blood rather fast while snorting through the nose. Other routes are inhalation. So if we look here in the tissue, the drug is in the air inside the lungs, and the tissue lining the lungs is very thin, much thinner than even the small intestine. So drugs have a very easy time getting into the blood through inhalation. So through all of this, we're talking about whether or not a drug is ionized or very polar. And because of that ionization or polarity of the drug, it's not able to cross the fatty membrane that surrounds the cells. So drugs with full charges have a really hard time getting into the blood. So usually those types of drugs need to be injected directly into the bloodstream. If you have a drug that is not charged, it can get through the skin, but it will do so at a very low rate. And not many people will abuse drugs that way. Okay, so that is the drug getting into the body. Now, where does it go after it's gotten into the body? So we're now talking about the distributive phase. So the drug is increasing, you're absorbing it into your body, and it's starting to spread throughout all the tissue. The absorption is starting to run out because you're absorbing almost all of the drug, and it's diffusing out into tissue. So this graph levels off and forms a little plateau. So this comes to our second question. We are talking about drugs in the body, and I keep making a point about saying the drug concentration in the blood. But probably not as relevant in this discussion. But do we really care about the drug being in the blood? Is that what makes someone high? Does it matter what the concentration of a drug is in the blood? And if not, where does the drug have to go in order to make someone high? If anyone can put that in the chat, we can see what you're thinking. It does get into many different tissues, but which tissue is needed, which tissue needs to have the drug in it in order for someone to be intoxicated? There you go. We have Jennifer. You are correct. It is the brain. The blood actually doesn't matter a whole lot if there's drug in it. What really matters is whether or not we get drug into the brain. So we've got two drugs that really bring this point home. When we talk about antihistamines, there are the older Benadryl type of drugs, which you take that antihistamine and it works. Maybe you're not sneezing as much, but you're getting really drowsy and you might just fall asleep. And in fact, Benadryl is used to put people to sleep for certain conditions. Now we have newer antihistamines like Claritin, which are non-drowsy. And you can take them, you're going to stop sneezing so much, and hopefully you're not going to get drowsy. And the reason that they don't cause drowsiness like the older drugs, the Benadryls, is because Benadryl can get into the brain, but Claritin cannot. So they're both in the blood, but whether or not it actually gets into the brain can make a drug of abuse, where some people do abuse Benadryl, versus Claritin, which there's no point in trying to abuse Claritin because nobody will get high off of that. In the more illegal realm, we have heroin. Heroin is a much stronger drug than morphine. They both have the same effect on the body, but heroin is able to get into the brain much faster. And by getting in faster, you're going to get a higher concentration of that drug into the brain than you would for morphine. So we get lots of people who are addicted to heroin and abusing heroin, and not nearly as much who are addicted to morphine, because that high is not as strong because it doesn't get into the brain as easily. So now we're going to look at the brain. How do the drugs get into the brain? And we're picking the brain out because that's where the drugs have an effect. But also, there's a type of tissue called the blood-brain barrier. And these cells that are lining the brain have special junctions between each other that prevent drugs from getting in. It makes it much harder than other tissues. And so, so again, you've got a drug with an electrical charge or a polar drug, and a drug with no polar charge. And the drug without a polar charge is able to diffuse through these fatty layers lining the cells, whereas the drug with the charge has a much harder time getting in. So you can have a Benadryl without a charge, or a Claritin with a charge that doesn't make you drowsy, or that makes you drowsy, depending on whether or not it gets into the blood. Now, drugs will also diffuse into body fat, which can be very important for certain drugs, especially marijuana. So drugs that are not polar, they don't like water very much, but they do like other fats and greases, such as body fat. So what you can get is the drug is in the blood. Again, it has tissue to cross before it can get into the fatty tissue. But if the drug is nonpolar, it has no trouble getting through the cell membranes into the fatty tissue. Since the fatty tissue is not polar, the drug loves to sit there. It's much happier to sit in the fat than it is in the blood, which is mostly made of water. So you get a higher increase of the drug into the fat and a lower decrease of the drug out of the fat into the blood. And what that sets up is someone can use marijuana on day one and then still have THC, the active ingredient in marijuana, which is very nonpolar and loves fat. It can sit in there for months, and you can still test positive for marijuana use months after you actually used it. So this can cause a problem with what would really be like a false negative test. Saliva is also a place where drugs can get into. There are blood vessels lining the mouth and the salivary glands. Drugs can diffuse from the blood into the saliva, and saliva can also be a component of, a tissue where people are looking at to detect drugs. Similar to saliva is hair. We have blood vessels lining our hair follicles. So here, this is a hair follicle, and the hair grows right at the end of the hair follicle, and that is lined with lots of blood vessels. As drugs are in the blood, they can then diffuse into the newly formed hair. Once it gets into the hair is continually growing. So new hair is going to form after the drug is gone, and that's going to push the hair out of the scalp. So you can take a drug on one day, it'll get into the hair, and then as the hair continues to grow, that section of hair with the drug then gets pushed out and onto the surface of the head and moves further down the length of the hair. There can be a complication in that where you don't just get drug incorporated into the hair at the origin of where it forms. You can also get drug into the hair from sweat and oil. So the drug is going to get into sweat and oil glands, get into the sweat and oil on the surface of the skin on the scalp, and then that will coat the hair, and some of it can diffuse into the hair as well. Then we have fingernails and toenails. Again, anywhere that you've got blood vessels supplying a tissue, you're going to be able to get drug to it. So fingernails, they start growing at the cuticle and they push out towards the fingertip. So you've got drug in the blood vessels near the cuticle. It will get incorporated into the fingernail. And then as the fingernail continues to grow, it will push the section of that fingernail with the drug out towards the fingertip. And also similar to the hair, you've got blood vessels surrounding the fingernail on the bottom surface of the fingernail. And drug can also diffuse out of the blood and into the fingernail from underneath. Drug distribution can also go beyond the initial person of interest. If we have someone using drugs who is pregnant, then drugs will go from the mother's blood into the placenta, which feeds blood to the fetus. So then you can get drugs ending up in the umbilical cord blood, as well as the fetus's hair, if it has hair. And it also ends up into their intestinal tract. And the meconium, which is a stool that forms in the fetus while it's still before it's born. So that's where the drug goes once it gets in the body. The body wants to get rid of that drug. So now it's going to try to eliminate it. So here we're going to be talking about the last phase of this drug concentration curve, how the drug is going to get out of the body. The main way is going to be through the kidneys. That's because the kidneys get about 25% of the cardiac output from your heart. So there's lots of blood pushing through the kidneys. And the kidneys are very good at getting water-soluble drugs out of the body. And since most drugs have to dissolve into the blood to get into your body, they're going to have some ability to dissolve in water. And those drugs that have a very low solubility in water are going to be changed to make them more water soluble so that they can be removed from the kidneys because it has such a high capacity of removing drugs. So the reason the kidneys work so well is because of the glomerulus of the kidney. And if we look at that tissue, it's different from what we've seen so far. Before, the cells lining different tissue all butted up together and they formed a seal, forcing drugs to go through the cell membrane, so having to go through that fatty layer in order to cross through the tissue. But in the kidney, in the glomerulus, you don't have that. There are gaps between the cells lining the glomerulus. And what this does is it lets any drug to go through, any drug that is water soluble, whether it has a charge or no charge, go right on through into the urine from the glomerulus. So this makes it much easier for the body to get rid of drugs. And it also gives the body an incentive to try to make drugs more water soluble, because then they can go from the blood to the urine much easier than other routes of elimination. We'll talk about that right now. So if a drug is not water soluble, something like THC and marijuana has a little bit of water solubility, but it's very low. If you have that situation, then the kidney is not going to work very much because there's not a lot of drug in the blood to go out and form urine. So remember when I was talking about soap early on, the body actually produces its own form of soap to deal with these non-polar, not water-soluble drugs, just like we use soap to wash our hands. So if we zoom in, this brown blob is the liver. Blood is coming into the liver. Inside the liver are tissue that makes something called bile salts. Bile salts are basically a form of soap. The bile salts then collect in the gallbladder, and there's a tube leading from the liver, the gallbladder, into the small intestines called the bile duct. So you have a drug come into the liver. It then gets dissolved into the bile salt. So that here we've got THC from marijuana. It's inside the fatty blob of the bile salts. And it can then go into the intestine and get flushed away. The problem is this path is complicated by the fact that the bile salt soap is meant for absorbing nutrients from food. It's not meant so much for getting rid of drugs. And I can say that because the bile duct connects to the small intestine close to the beginning of the small intestine. So its job is to help things get absorbed, help fatty things get absorbed into the blood from the intestine. So what happens is when drugs get into the bile salt and get into the intestine, they can actually get reabsorbed right back into the blood. So this is termed hepatic recirculation, where the drug is excreted into the bile, gets to the small intestine, gets taken right back up into the blood, and then out through the liver again, out into the intestine, taken back up in the blood. So what it can do is makes the drugs that do this, mostly the non-polar drugs, stick around for a long time because the rate of elimination is very slow since they keep getting reabsorbed. So now if you have a drug that is volatile, such as alcohol, it can then get eliminated through the lungs. So we showed before there was a very thin layer of tissue between the lungs and the blood that can help things absorb, but it can also help things get out. So as someone exhales, the drug is going to leave in a vapor in their breath. The last component of elimination is through sweat. We have two types of sweat. One sweat is sensible sweat, where you produce lots of liquid that gets on your skin and you can feel it. So that is termed sensible sweat. You can sense it, but it's there because you can feel that liquid. And then there's insensible sweat, where you're constantly producing a tiny amount of sweat all the time, and it's able to evaporate very quickly before it pools and forms liquid layers, so you don't really sense it. So it is called insensible sweat. And drugs with that vaporize very easily, like alcohol, they can get eliminated through the insensible sweat. So just to summarize the pharmacokinetics so far that we've learned, how drugs get into the body, where drugs go when they're inside the body, how the drugs leave the body, and then the effects of electrical charges or chemical polarity on the movement of these drugs in the body. Now we're going to look at metabolism. and what the body does to change the chemical structure of drugs. So there's two main functions that metabolism serves. It is one, to inactivate the drug so that it no longer gets a person intoxicated, and it also speeds up the elimination of the drug, primarily through the kidneys, by making the drug more soluble in a way that makes it more polar or adds an electrical charge to it. So because you're converting the drug to another chemical called a metabolite, the concentration of the drug itself will decrease in the blood. So the effect of elimination as well as metabolism will cause a decrease in the drug concentration in the blood. Although with metabolism, you'll then get an increase in the concentration of metabolites. So most metabolism occurs in the liver. That's mostly because the liver is a pretty large organ, and it has lots of enzymes that will cause the metabolism to occur. But really any tissue just about has the ability to metabolize drugs. It's just that the liver is really the main workhorse. So what happens is metabolism is a two-step process. You've got phase one, where the drug gets reacted with an enzyme. The enzyme chemically changes it into a metabolite, primarily by adding a polar group to it. And as we saw with the chemicals that we were talking about in the very beginning, that usually involves adding an oxygen. That oxygen just loves to pull on electrons, so it's going to cause polar bonds in that molecule. Then the drug is going to enter into phase two, where instead of changing the drug that's already there, we're going to add a chemical that already has charges or electrical polarity to the drug. So it's changing the drug as it is, and then we're adding something to it. And as the drug goes through this process, it's making it more electrically charged, which is going to speed up elimination through the kidney. So here's an example. We have THC. It has two oxygens on it. So it has a little bit of polarity in it from the beginning. And it goes through one reaction and turns into 11-hydroxy-THC. That adds another oxygen to it, making it a little bit more polar. Goes through a second reaction, making it THC carboxylic acid, where it's adding two oxygens onto one carbon. What that does, as we saw with the fatty acids, this is the acid component of a fatty acid. This oxygen is going to pull on the electrons of this carbon, and this oxygen wants to pull on those electrons too. But since this oxygen is already yanking electrons away from the carbon, this oxygen has a lowered ability to pull the electrons away from the carbon. So instead, it pulls electrons away from the hydrogen. And what that can do, oxygen as it's stronger, much stronger than the hydrogen, and having two oxygens pulling on electrons at the same time, you can actually ionize that hydrogen, where this oxygen just rips the entire electron away and tells hydrogen to go play somewhere else. I've got your electron and you're not getting it back. So this then adds a full charge to the THC molecule, making it much, much more water soluble. So that all encompasses phase one. Now we're going to add a glucuronide, which is a type of sugar, to this next enzyme, And the glucuronide comes with lots of oxygens all over the place. So now, with the THC, carboxylic acid, glucuronide, we have oxygens all over the place. And so this drug is much more water soluble than it used to be. It's got two carbonyl groups, and this one can then ionize again and making a full ion charge. So the whole process is just making things more water soluble. And the different phase 2 chemicals that can be added to the drugs include glutathione, which, as you can see, has lots of oxygens in there, also some nitrogens. Sulfation, which adds 4 oxygens, all pulling on electrons. Glucuronidation is a sugar, which is coated with oxygens all over the place. And then acetylation is kind of a weaker conjugate. It only has 1 oxygen, but it still helps make the drugs more water soluble. So with metabolism, we've got the effect of also inactivating the drug. So you're changing the drug to such a degree that it no longer can cause intoxication. So here we've got in blue the active component ethanol. It gets converted to acetaldehyde and acetic acid. Both are in red, indicating that they're inactive. Cocaine gets converted to benzyl agonine. Benzyl agonine is inactive, but the cocaine is active. Sorry. Here we've got THC, which is active. It gets converted to hydroxy-THC, which is still active. And it's not until it gets fully converted to THC carboxylic acid that it becomes inactivated and no longer causes intoxication. Now we've got the opposite. So before, we've had a drug that is active going to something that is inactive. Now we're going to look at heroin and codeine, which are really termed prodrugs because they're not active in their current form. They have to be converted to morphine to become intoxicating. So heroin itself needs to first get metabolized to monoacetylmorphine and then to morphine. And codeine goes directly into morphine. The morphine can then get metabolized further into hydromorphone, which is also active. And in fact, not only is it active, it's more active than morphine. So hydromorphone is also a drug in itself. Some people may know it as Dilaudid. It is not quite as strong as fentanyl, but it is a very strong opiate. And then in this case, it's kind of unusual. Morphine can get glucuronidated where it's got that big bulky sugar onto it and still be active. Most drugs, when they get glucuronidated, will not be active because it so drastically changes the chemical structure. But in this case, with morphine, it is still active. Diazepam is a very weird drug. It starts out active, and then it gets converted to nordiazepam, which is inactive. But then nordiazepam gets converted to oxazepam, which becomes active again. And then oxazepam gets glucuronidated, which is inactive. So you can go from active to inactive and back and forth several different times. Or you can have something like methamphetamine, which gets converted to amphetamine, and both are active. It doesn't, neither one of these are the inactive. So drug metabolism adds some complexity into how these drugs work. But you also have issues of the speed of metabolism and what you can actually detect in different tissue. Excuse me. So drugs that are not easily detected are going to be shown in black, such as heroin and cocaine, whereas drugs that can be detected easily are shown in red, or their metabolites. And the reason for this, heroin gets converted to monoacetylmorphine very quickly. So by the time someone injects heroin and someone is around to take a blood sample and measure if there's heroin in their blood, the heroin's already gone. It's fully reacted to monoacetylmorphine and morphine. Same thing is true, but to a less extent with cocaine. Cocaine gets converted to benzoyl very quickly. In so many cases, you may not see the cocaine at all. You may only see benzoyl. Then metabolism can, as we said, speed up elimination of a drug, but it can also slow down elimination of a drug in some ways. So you've got, we just talked about how metabolism can be fast so that you can't detect that drug, but here we can get metabolism that slows things down so that you can better detect a drug. So ethanol gets eliminated relatively quickly over a few hours. Most of it gets converted to acetaldehyde and acetic acid. But there is a minor amount that will go through a different metabolic pathway where it can get converted to ethyl glucuronide, ethyl sulfate, or fatty acid ethyl ethers. And these can be detected for days. So the alcohol could be gone from the system, but these minor metabolites can still be around and can be used to look at alcohol use from several days prior. Similar with THC, again, as it likes to get stored in body fat, we've got THC and its metabolites coming into body fat, slowly coming out. And as over time, the THC will get converted mostly to THC carboxylic acid. And then you can measure THC carboxylate for weeks, and in some cases, depending on how frequently the person uses marijuana, it could be months later. So, talking about metabolism isn't just important for what to detect, it also is important in how you interpret a drug test. So, if you were to get a drug test and it says, we detected cocaine, but we didn't detect any benzoyl, or we detected THC, but there was no THC carboxylic acid. Anytime you don't have a metabolite for a drug that normally forms a metabolite, it makes you question that test because something didn't happen right. What you may be happening is you are picking up environmental exposure. And we'll talk about that a little bit more with hair, but you can be around someone smoking marijuana or crack cocaine. The THC or the cocaine gets vaporized into the air and collects onto the hair. You may have never consumed those drugs directly, but just being around in that environment, the drug can get into your hair. But when you get the results from that positive test, what you're going to see is just the cocaine or just the THC. You're not going to see the metabolites. So if there are no metabolites, what that means is the drug never got into your body and never got to your liver or other tissues to be reacted with to turn into the metabolite. And so it indicates some type of environmental exposure. So it's always a good thing to look not just at the drug levels, but also whether or not metabolites were formed. So with metabolism, we learned that it speeds the elimination of a drug, mainly through the kidneys by making it more water soluble. It can inactivate the drug, although in other cases, it actually activates the drug. Also, the speed of metabolism depends on which drugs you can detect, and whether or not metabolites are present will help you interpret the results. So we are about halfway through, so maybe we should go ahead and take a short little break and meet back in about 5 minutes.
That sounds great. So we'll be back at 2:31, and a couple of questions have come in, so we can look at those when everyone gets back.
Okay.
Thanks. You ready for some questions, Dr. Evans?
Yeah, I was just looking through some of these.
Okay. Yeah, I think you've started to address, or I think you've addressed parts of many of them. The first one was about like a timeline for when drugs start to take effect. Do you have, I don't know if the person wants to know about a particular drug or if you know of a resource where attorneys could look to find that information for different drugs.
Well, the speed that a drug affects someone, so that's going to depend on several things. One, the actual drug, and then two, how the drug is taken, and then three, the concentration of the drug. So if you've got, we'll say, morphine, you can try to smoke it and it'll get into the blood pretty quickly and start to have its effect pretty rapidly. You can inject it and then it's instantly in the body and it's going to have an even faster effect. But then if you were to eat it, it would take a lot longer to get into the body and a lot longer before it has its effect. Now you go on to something like a patch, which is really not used for morphine, but for fentanyl. That's absorbing through the skin, and that could take hours before it starts to have effect. So the route of administration really plays a big role in that, probably more than the actual drug itself.
Okay, thanks. The next question was about hair testing. So when a hair test is done and shows both the drug and its metabolite, what is the relationship?
So if you're seeing both the drug and the metabolite, then it's saying that the drug was inside the person's body. They did consume something. There may be some drugs where the ratio of drug to metabolite is different from what you would see in the blood and the hair. But I can't think of any where you wouldn't see at least one metabolite in the hair. Well, of a drug that you would see metabolites with. There are a few rare drugs that don't really metabolize too much.
Okay. The next question was, could there be metabolites from environmental contact? So like if a child's parents smoked pot and the child breathes in the marijuana smoke, he's not using the drugs, but could he still have the drugs and the metabolites in his hair from environmental exposure?
Well, I guess there's two components to that question. One is you've got the parents are smoking the drug. We'll say it's, what did they say, marijuana? We'll say it's marijuana. The parent, it goes into their lungs, into their blood. The marijuana gets metabolized into their blood, which then goes back to the lungs. And you could get a very, very tiny amount of metabolite into the air that they're breathing out. But we're talking minuscule amounts. So the ability to get a metabolite into hair from an environmental exposure is really low. There are several companies trying to develop a breathalyzer for marijuana, but it's very difficult because the amount of marijuana that's in a breath is just super small. The other component to that could be if the person is breathing in the THC and from just in the air, and they're metabolizing some of what they breathed in. And so there you get the THC as well as the metabolites in the hair. That can happen, but usually, maybe Dr. DeCall will talk about this tomorrow. Usually drug tests have what's called a cutoff level. So it's not indicated as being positive until the concentration of the drug has reached a certain concentration. And they set those cutoff levels, those concentrations, to a point where something like that shouldn't cause a positive test. So it could happen, but there have been many studies looking at secondhand marijuana smoke, and it's pretty hard to get that kind of an exposure.
Okay. And then the last question we've gotten is about the levels of metabolites and if they're reported. So can you find the level of the metabolite in the report so that you could try to figure out if the drug was ingested or environmental?
As we'll find tomorrow, lab reports are not standardized, and every company has their own setup and how they report different things. Some of them, they will report metabolites and some that won't. Whatever you get as an initial report, you really should request the litigation package if it's an important test to you. And the litigation package should include all the details of that test, and hopefully would also include metabolites. But I'll have to say, even litigation packages vary from lab to lab. You can get really good ones that are clear and detailed, and some that are not so good. So it's there's not one easy answer.
All right, thanks so much. Those are all the questions we have. So we'll let you return the presentation, and for the attendees, please keep putting your questions in the chat and we'll ask them on the next break.
Okay. Okay, so we've learned about how the drug moves throughout the body, different factors that influence that, electrical charges, some chemistry. Now we're going to move into the drug testing. And the first part we want to ask is, what specimen are we going to test? And that depends on the characteristics of those tissues, which depend on drug distribution and elimination. So this table shows different specimens and whether or not that type of specimen allows itself to be retested so that you can challenge the initial test in court, whether or not the collection of that tissue is observed by somebody other than the client, and whether or not that tissue can be tampered with. And this is really my own subjective level of tampering, but we'll talk about some of the ways to tamper with these specimens. So I split this up into 3 different categories. On the top, we've got current use. So these specimens will detect current use of drug. These are really good for things where you need to know if the person was actually impaired, like DUIs, things of that nature. Then there are specimens that will look at recent use of drugs, as well as some that look at distant use of drugs. So blood, including umbilical cord blood, is for current use. They can be retested and challenged in court. The observations are observed, and because they're observed, there's a very low ability to tamper with them. Breath is not kept. Usually when you're blowing in some type of breathalyzer, there's a vent at the back of it, and all that breath just goes out into the room. So these cannot be retested and challenged in court. In cases of probation, breath samples can be done without being observed. But something like a DUI that would be observed. There is I would say, a medium chance to be able to tamper with breath tests, and we'll talk about that later. Saliva can be collected and retested. It's usually observed by the person collecting it, and I'm giving it a low ability to be tampered with. Specimens for recent use include sweat as well as urine. The liquid forms of these, the urine and the liquid sweat, can be retested and challenged in court, but sweat vapor is very much like breath. It's not collected, and that cannot be retested. Urine is usually not observed, the urine collection, but in some cases, usually if there's been a problem with collection or someone is accused of tampering with their urine sample, there can be an observed collection with a person of the same sex doing the collection or observing the collection. Urine has a very high ability to be tampered with, and there's many federal regulations on urine testing to kind of look at attempts to tamper with it. The sweat tests usually are not observed because they are long-term tests that may occur over days, and they have a much lower ability to be tampered with. Distant past drug use would include hair and nails. And hair, you can either use hair from the head, but as we'll talk about later, you can also use body hair, and that can help reduce some of the ability to tamper. Fingernails and toenails don't have a high ability to tamper with. They're very solid material. So even if you're able to cause some damage to the surface of it, the material in the center of the nail is going to be much less affected. And meconium, this is the feces that's formed in a fetus and is collected with the baby's first defecation, where they will use a diaper and collect the first poop from the baby and check that for drugs. That is observed by hospital staff, so it's very low ability to tamper something like that. Well, we just started, so unless anyone has any burning questions, I'll keep going.
I think we're good to go.
Okay. All right. So we talked about which tissues to look at for drugs. Now let's talk about how you actually detect those drugs. Drug detection is in two phases. You have a screening phase or screening test, and that is followed by a confirmation test. And screening tests are usually cheaper and faster than confirmation tests, and they are able to detect drug classes but not specific drugs themselves. So if If you're looking at heroin use, they will show up use of opiates, but a confirmation test can look at the very specific drug that you're asking about. So they would show up as monoacetylmorphine and not just opiates. Screening tests can be used in the field. Hospital tests are usually on the level of a screening test. It's pretty rare that a hospital would use a confirmation test. Their interests are very different from forensic uses. The screening test, because it's looking at classes of drugs and not specific drugs, the test is not run so that it compares the specimen to a known drug in a screening test, but that is done in a confirmation test. So if you're looking at monoacetylmorphine to detect heroin use, the confirmation test is going to have a known standard source of monoacetylmorphine, and it's going to run that with the test so that you can compare. You know this is monoacetylmorphine. You don't know what this is, but it looks like monoacetylmorphine. Because you can compare them, it makes it much easier to say, yes, what we detected was monoacetylmorphine. And screening tests usually do not get into court except for some civil cases or limited use in criminal cases, like to show probable cause, but nothing past that. You really need a confirmation test to bring evidence into court. So the reason that we have a two-step process for drug testing is basically for time and money. The screening test is going to look to rule out mostly the negative test results. So most of your cases are going to be negative. So we're going to do a quick and dirty test to get rid of those negatives. And then all of the positive tests shown here in red are going to then go on for confirmation testing. So it's just because the expense and the time of confirmation tests is higher than the screening test, it's actually cheaper and faster to do it as a two-phase approach. So screening tests, you can have either field tests or at-home tests, things that are not analyzed in the laboratory, or you can have laboratory tests as well. Dr. DeCall will talk about laboratory tests tomorrow, and I will talk about the field and home tests. So we're going to talk about three things: dipstick drug tests, the SCRAM alcohol monitoring system, and ignition interlock tests. Not really tests. Well, it is a test. But it's also a device to keep people from driving while impaired. So the urine dipstick test is technically called a lateral flow immunoassay because this is an antibody-based test. Antibodies have a relatively high rate of false positives. These are the tests where you can take something like ibuprofen and it will look like marijuana to the test. And as I said, with the other screening test, this identifies drug classes because of the fact that it's basing this on an antibody test. Urine is usually not observed, and these dipstick tests will give really quick results within minutes. And it's basically does not give you a quantitative result. It won't say how much drug was in the urine. It'll just say whether it was present above a cutoff level that they've designed into the dipstick device itself. So basically, it's just going to give you a positive or negative result. And these can be confirmed if the urine is kept, so that they can be retested and challenged in court. But if this is something, it really depends on how the test is done. Sometimes the urine might just be thrown out after the dipstick test. You really want to prevent that and keep that urine so that you can re-challenge or challenge those test results. So this is a picture of an antibody. An antibody is a complex protein molecule. It is composed in yellow of a variable region, which this is the part that binds to drugs, and then a constant region shown in green that is just pretty much the same for all antibodies. So only the drugs are going to bind to the variable region, not so much the constant region. So all proteins are a string of amino acids, and amino acids are chemicals that can have different electrical charge characteristics. Excuse me 1 second. So we've got amino acids with a positive charge, shown in red, amino acids with a negative electrical charge, shown in blue, amino acids that are mildly nonpolar in green, and that are highly nonpolar in brown. And they form these three-dimensional structures that can have little pockets, and inside the pocket, depending on which amino acid is there, will give different environments that are useful for some drugs to bind into. So here we'll look at amphetamine. This portion of the amphetamine molecule is very nonpolar, so it's going to be attracted to the nonpolar amino acids. This portion with a positively charged nitrogen will be attracted to the negatively charged amino acids over here. So it forms this pocket environment that is able to fit drugs that have a similar shape and electrical charge to them. So this is amphetamine, but you can also get similar drugs like methamphetamine. So methamphetamine is just like amphetamine, only it has this methyl group to it. It doesn't really change the structure too much, so these can also fit inside the antibody. That's not so bad because methamphetamine and amphetamine are very similar. One's a metabolite of the other. Who cares if we're detecting both illegal drugs? But that can then extend to something like pseudoephedrine, which is just cold medication and is fully legal to take. It has this hydroxyl group, but it may also fit nicely inside this pocket. So here you could get a false positive test for amphetamine with pseudoephedrine. So this is what a urine dipstick test will look like from the outside. You've got this plastic housing with a little absorbent pad sticking out of the bottom, an indication window where you read the test results, and an example of the test results, and which help you interpret how the test goes. So it tells you how to figure out if it's negative, positive, or invalid. So if we take a look inside and look at the guts of this, you've got different layers of padding, of absorbent padding. You have the sample pad, which is dipped into the urine, and that allows the urine and everything in it to get absorbed into these pads and travel upward through the pads to the top with the absorbent pad at the end. And as it travels through, it goes through a conjugate pad as well as a capture pad. And the capture pad is going to have two lines. One is called the test capture line, and the other is the control capture line. But first, let's talk about the conjugate pad. There, it's going to have a protein that is conjugated or bound to a dye. In this case, this is a red dye, as well as cocaine. So the dye is there so that you can see where this conjugate is, and the cocaine is there to bind to the antibodies. And the antibodies are going to be placed on the test capture line. These are going to be antibodies that are specific for the cocaine, and the control capture line are going to have antibodies that are specific for the protein that was used in the conjugate. So what happens if you test urine without cocaine present? Urine gets placed in the sample pad. It starts to absorb into the rest of the device. That picks up the protein drug dye conjugate, and it travels upward to the absorbing pad. As those conjugates go past the test capture line, the antibody is going to bind to the cocaine on those conjugates, and that's going to give a line with the red dye at the T mark, the test capture line. The antibodies specific for that protein are then going to bind to that protein as well, and that's going to give a red line at the control line. So you'll have two lines, and we'll look up here to see how to interpret that. Two lines means negative, no cocaine present. So what happens if there is cocaine? So here we've got cocaine in the urine. Urine starts everything flowing, and the conjugate containing the cocaine on the outside will compete with the antibodies on the test capture line for the free cocaine in the urine. So if the concentration of cocaine in the urine is higher than the concentration of cocaine on the protein conjugate, then it will prevent the protein conjugate from binding to the test capture line. So you get just the free cocaine binding to these antibodies and no line at the T. The control line is just to make sure that the test is working, since it's only binding the protein of the conjugate and doesn't care about cocaine. So if you get one line, the control line, see that we interpret that as a positive result. And we've got another interpretation. That is an invalid test. Say something goes wrong. Maybe the person donating the urine somehow puts bleach in their urine, which disrupts the proteins in the antibodies so that they're no longer binding. And in that case, you would get no binding on either the test line or the control line. You get no lines in the window, and that's interpreted as an invalid test. So the invalid test is going to show you that something happened that damaged the test, but it's not going to tell you what happened. So in a case like that, you would really have to just test a second time. So what we learned with the dipstick test is that They can be confirmed and retested to challenge in court if the urine is kept. But that's a procedural difference, so whenever possible, keep that urine so you can contest those results. Sometimes these are observed collections, but usually they're not, and that allows for people to easily try to tamper with the evidence. And because the dipstick tests develop in just a few minutes, these give very fast results. So now we're going to talk about transdermal alcohol. So this is basically a device that is the same as a breathalyzer, but for your skin. So alcohol will be eliminated through sweat, as we said before. It's a minor pathway of elimination. It's only about 1% of ethanol will come out through the sweat. And the amount of sweat that people produce will vary between different people, between locations on the body, different environmental conditions. Is it hot? Is it cold? The person's hydration. If they're dehydrated, they're not going to produce as much sweat. And the device that I'm going to talk about today is detecting the insensible sweat, the vapor sweat, not the liquid form. And this is called a SCRAM. The company is called SCRAM, Continuous Alcohol Monitoring Input. So as you can see in this picture, this is a plastic device that is strapped to the person's ankle, and it can remotely detect alcohol. What it does is, like I said, it's basically a breathalyzer. It sucks air in from around the skin and analyzes it. It does that every 30 minutes, and it uses the same fuel cell technology as the preliminary breath tests that police use for DWI out on the field. So again, this is a screening test, not a confirmation test. Since the air is pumped through the machine and vented out, it's not collected, so this cannot be retested. Some of these instruments have GPS location capabilities to monitor the location of the person. And the manufacturers say to not use anything that contains alcohol in these devices, such as hairspray or perfume. But then it also says that it's able to tell the difference between environmental alcohol and consumed alcohol. So this uses a fuel cell detector. The way the fuel cell works is it has two metal catalysts. And a catalyst is much like an enzyme. It is something that speeds up a chemical reaction. The chemical reaction that's going on is alcohol from the breath is getting converted to acetic acid. During this conversion, it produces an electron. So an electron is given off during this reaction. That electron follows a wire connected to the other catalyst. The other catalyst catalyzes the reaction of oxygen turning into water, and it uses that electron. So it sucks that electron up into the oxygen to help it convert to water. And as the electron is moving from one catalyst to the other, that electrical movement can be measured by the instrument. So what it outputs The manufacturer terms transdermal alcohol concentration, or TAC. But this should not be confused with BAC for blood alcohol concentration. These are not equivalent units. The TAC is really looked at semi-quantitatively. That means it gives you a number, but to interpret it, you're not saying you had a TAC of 0.1, you would then interpret it as either a high, medium, or low. So it's more of a categorical interpretation. And there are several reasons why the transdermal alcohol concentration is not the same as a blood alcohol concentration. The TAC is usually lower than a BAC. There's a delay in when the level of the TAC starts to increase after someone starts drinking compared to a BAC. And there's also a delay in that level decreasing back down to 0 compared to a BAC. The SCRAM company has a policy to try to limit false positive results, in that it only considers a positive result when the TAC is above their cutoff level for 3 consecutive measurements. So it takes a measurement every 30 minutes. So that would mean that the TAC has to be elevated for an hour and a half above their cutoff level, which they say is over 0.02%. And the company claims that this is a level that would not be reached if the person consumed 1 standard drink. And they also say that this would not be reached if you were to have food that had alcohol in it. So they claim that their false positive rate is less than 0.1%, and that in the inverse, they have a high false negative rate of 21%. So they are claiming that they're doing what they can to prevent false positive results. So they said to make sure alcohol in the environment is not a problem, that you're not using hairspray or perfumes around it. But they also say that they can detect if that's what happened. So because you have to have 3 time points with a high level of alcohol in order to be considered positive, if you only get 1, that indicates that it was probably just a transient environmental exposure to alcohol during that time. And so they will not count that as a positive result. And they also claim that they have 2 people interpreting the results to help lower errors in interpretation. These instruments also have features that will detect if the instrument has been tampered with. They measure the temperature outside of the instrument to make sure that a warm body is wearing it. They have an infrared sensor that will check to see if anything is obstructing the machine from the person's skin. So if you try to put like a plastic coating, maybe like saran wrap or something, to block the instrument from reading the air next to the skin, it will detect that. And there's a sensor in the strap around the ankle. So if it's cut off, that will be detected. So you could tamper with this instrument probably only in one way, and that would be with fresh air. So there is a small gap between the instrument and the skin. So if air were to be blown through that gap right at the 30-minute time interval that it is measuring alcohol, then you could probably reduce the reading of it. But that could have the effect of cooling off the skin, which it would then detect as a change in the temperature. So it may work, it may not work. I haven't actually gotten access to one of these devices to test it. But that seems to be probably the only way that you can tamper with it without caught. So to summarize, the SCRAM continuous alcohol monitoring system, they cannot be retested or challenged in court. They try to eliminate false positive results by the policies of the company, but their policies, they could always change however the company wishes to. They are supposed to be tamper resistant, and this is remote monitoring, so the information doesn't just stay with the anklet, it gets transmitted to the monitoring company so that that information is not lost if the person were to detect positive. So now we're going to talk about a similar system, the interlock, ignition interlock system. This is also a breathalyzer that is installed in your car, and it is done to prevent people who have a high risk of drinking alcohol and driving. It allows them to where they can still drive as long as they are not drinking. So it works at 2 time points. One, you have to blow into the instrument when you're starting your car, and if it does detect alcohol above whatever cutoff is set by the agency who required it, then it will not let you turn on the car. And then once you start driving, if you start driving for about an hour or so, it will require you to keep testing at a random interval while you're driving. And what they say, there's actually 3 companies that are approved to sell these in North Carolina. 2 of them say that you have to pull over, get off the road before you can take a random breath test. The one company is claiming that you can just keep driving and take your breath test while you're driving, which probably is not the safest thing to do. If you are driving and the breath test tests positive for alcohol, they realize that it would be dangerous to just shut off the car's engine while you're driving down the road. So it will not do that, but it will tell you to pull off the road and take a second test to verify those results. And it says that when you do that, when you pull off the road, you're supposed to turn off the engine, so that then if the second test shows alcohol, then you can't turn the engine back on. But they realize that it would be dangerous to just shut the engine off in the middle of driving somewhere, which is good. You also need to periodically bring the device into a service station to get data downloaded from the device, and I think to check and make sure it's functioning correctly, properly calibrated. There is a way that if the instrument does lock the driver out, that they can call the monitoring company and get to reset and unlock the device. And there are also problems in cold regions where the device may not work if the temperature is too cold. So they claim you need to hold it in your hands and physically warm up that device before you can turn on the car. Some of these will have GPS systems to it, so they can track the location. And they try to make sure that the person is not using like a balloon with air attached to the device just to blow fresh air through, because they have the option to either require the person to initially blow air and then inhale air and then blow again, and then the measurement is taken on that second blow. And that's just to say that you have to be at least a human in order to do that, to make sure you're not tampering with the instrument. Another alternative method, mostly I've seen this in North Carolina, is they have it so that it can detect if you're humming, and you're supposed to blow air and hum at the same time, and that will say that you are a human and not using like a balloon to just blow air through. Another way to confirm, not only is it a human blowing into the instrument, but is it the correct human? So you can't have an intoxicated driver and a sober passenger and have the passenger blow into the machine, because many of these devices will have cameras that will take a picture of whoever is blowing on the machine. And if it's not the right person, then it will not unlock the car. And what they do is they can have facial recognition software, so that when you first set up the ignition interlock, they'll take a picture of the person and put that into the machine, and that helps calibrate the facial recognition software, so that when you go to test again, it will be able to determine that it's you and not someone else. There is a problem with mouth alcohol, that you are supposed to not have anything in your mouth for 5 minutes before the breath test. And they also advise you to rinse your mouth with water before taking the breath test. And the reason that's a problem is because these instruments don't have what's called as a slope detector. And let's explain what a slope detector is. So with mouth alcohol, if the alcohol is shown here as this little blue cloud, if it's located in the mouth instead of deep in the lungs, what you get is as the person starts to blow, the alcohol gets into the instrument right away, because that air is right where the mouthpiece is for the instrument. So you get an immediate high level of alcohol reading. If the alcohol is in the blood, most of the air in the mouth doesn't have alcohol. The alcohol is mostly in the lungs. So as you start blowing air, that initial air is not going to have alcohol in it. And it's not until at the end of the blow that the alcohol level starts to increase, when the alcohol is from the blood and out the mouth. And so if you graph these results, with alcohol on the y-axis and time on the x-axis. When the alcohol is from the blood, you're going to get a line with a slope that increases with time. But if the alcohol is in your mouth, you get the opposite effect. The slope is where the alcohol decreases with time. So some breathalyzers will have smoke detectors that can tell if the source of alcohol is from the blood or from the mouth. But ignition interlock systems, at least in North Carolina, have not do not have this feature. So things that can cause this mouth alcohol, everybody knows about mouthwash. That's the biggest one. But other things can cause mouth alcohol as well, such as bread made with yeast, flavoring extracts that have alcohol, including vanilla and almond. And oddly enough, natural citrus flavoring can have alcohol in it. So if you have something with orange, lime, or lemon juice, that can also cause a positive test on an interlock system. And there's a old wives' tale that if you put alcohol in a baked item, that, the alcohol will just bake off and there won't be anything left. And that's not always true. Sometimes that alcohol is still there. So something as benign as vanilla ice cream can set the interlock system off, and you won't be able to drive until you get a clean breath sample. And this is actually a research project of mine. Our company is looking at surveying different foods and items that you would put in your mouth for sources of alcohol. So this sandwich can cause a problem. You can tamper with these breathalyzer devices. Hyperventilation can be used. So when a person is breathing normally, breathalyzer devices are calibrated to deal with a normal rate of breathing. But if someone starts to hyperventilate, the air is coming in and out of their lungs, the concentration of alcohol in their lungs is going to decrease a little bit. And the instruments aren't usually calibrated to measure that. And so it can lower the concentration of the instrument's reading, the concentration of alcohol that the instrument is reading. The hyperventilation, though, only lasts for a few seconds. This is not something that could be done for a DUI case where the police officer is watching the person before they take the breath test. You would obviously see someone hyperventilating before the test, and the police officer would then tell them to stop. But in a situation like an interlock system, that could be done because it's not an observed collection. The evidentiary breathalyzers that police use also will detect hyperventilation because they also measure carbon dioxide. And carbon dioxide also decreases with hyperventilation. So those are the field tests. The last thing we're going to talk about is collection of samples for laboratory tests. We're going to talk about blood, hair, and nails. Not really urine. That'll be discussed by Dr. DeCall. So blood collection, probably everyone has experienced this. It is looking at blood, so that only detects current use of drug or alcohol, it is the easiest to then use for interpretation. Was that person intoxicated? It's not as much of a big deal for child custody or probation cases. For other cases, that is important. You're supposed to not use alcohol, disinfectants when taking blood, but in reality, the confirmatory tests are able to differentiate alcohol that is used for disinfection, which is isopropanol, from ethanol, which is drinking. Hair collection offers several advantages over blood collection. But there are also some complications with it as well. First off, hair isn't always growing. It actually grows in 3 phases. The anagen phase, where the hair is actively growing, is seen in about 85% of the hair at any given time. 7% is in the catagen phase, where the hair is still present, but it stops growing. It just sits there and hangs out for a little while. And then another 7% is in the telogen phase, where the hair falls off the head and is just not even present. This small percentage of hair in the catagen phase can actually extend the window of detection of hair, the window of detection of drugs in hair, because it's not growing, it's just sitting there, and it was growing at some point further back. And actively growing hair in the anagen phase usually grows about 1/2 inch per month. So we've got the hair coming out. It is growing and pushing hair out above the scalp, and scissors are used to cut the hair. A lot of these tests are called hair follicle tests, and that would imply that the hair is plucked out and that the follicle, the part inside the scalp, is also tested, but that is not the case. These tests do not pluck hair, they cut the hair. So the name follicle test can be a little misleading. So because you're cutting the hair and not plucking the hair out, there is a 10 to 14 day window from the time when the hair is formed to when it actually gets out of the scalp. So if you're looking at current exposure, current usage of drug, you have to give it about 2 weeks after before you collect that hair, or you won't detect it because it will still be inside the scalp. So environmental exposure, we touched on that before. You've got the smoke. Say someone is smoking marijuana. It's got, well, actually in this case, it's crack cocaine. There's cocaine inside the smoke. There's not going to be the benzyl agonine, just the cocaine, and that can absorb onto the hair and get detected in the test. Usually what's supposed to be done is the hair, after it's cut, goes through a washing phase. And if the test was done correctly, they will test not just the hair, but also the wash that was used to clean the hair. And so what you'll get is 2 things that you can look at. You can look at whether or not the hair itself has drug and metabolite, and whether or not the wash fluid has a drug and metabolite. And just to back up for 1 second, as we already stated, you would not detect metabolites in the smoke, just the drug. if it was an environmental exposure. So if you do detect metabolite in the hair, that was from what was consumed. So if you see drug in the hair and metabolite in the hair, then that indicates a drug was consumed. If you see drug in the hair and drug in the wash, but no metabolites, then that indicates an environmental exposure. If you only see drug in the wash and no metabolite in the wash, or no drug in the hair, then that also indicates an environmental exposure. If you were to see drug and metabolite in both the hair and the wash, then that's going to mean that the type of wash they used to clean the hair was so strong that it was starting to damage the hair, and the drug and metabolite was leaking out of the hair into wash fluid. So as I said, hair grows about half an inch per month. The typical hair test is done with 1.5 inches of hair, and that gives a window of drug use of 3 months. Depending on how long the strand of hair that they use, how long away from the scalp that hair is, it will give you different windows of detection. It's generally thought that going beyond 1 year is probably useful. That hair is so old, it's getting exposed to the sun, maybe some of the drug in the hair is breaking down from sun exposure. So after a year, that's probably when it is about as far as. So because hair is continually growing and it's basically forming this timeline of drug use, you can do some interesting things with it. So this is the typical hair sample looking at 3 months with 1.5 inches of hair from the scalp. It's going to pick up habitual drug use, someone who's taking drugs many, many times during that 3-month period. If you were to take 3 inches of hair, looking at a window of 6 months, and the person was only using drugs for 3 months, and you compare that result to the typical hair sample of 3-month window, then the concentration of drug in the 6-month window would be lower, about half lower than you would see with the 3-month window of time and the 1.5 inch of hair. So you can detect further amounts of time of potential drug use with longer strands of hair. But if that was a short window of time that a person was taking the drug, then you might just be diluting out the sample and making it harder to detect that drug. It's also, because of that same reason, not very good at picking up single use. So this would be in a case of like a drugged crime or drug rape, where there's only a one time that the drug was used. It can be detected looking at a 3-month window, but it's very hard to do that. And usually you would use other methods, which we'll talk about in a second, to try to look at a single use. And because you can kind of treat the hair as a timeline of possible drug use, if you're looking at potential drug use that wasn't recent, but further down, and you don't really care so much about what's been going on recently, you can take a section of hair that skips the most recent amount. So you can determine. Yes.
you move your microphone a little closer to your mouth? You're fading out occasionally.
Oh, sorry about that. Is this any better?
That sounds good. Thanks.
Okay. So you can determine what time frame you're going to look at by what segment of hair that you actually test. But also realize that that is really a general rule, because drug can get incorporated into the hair through sweat and oil that bathes the outside of the hair. So there is still a possibility of some drug to be on the full length of hair. So say you want to look at a single drug use. You have a rape case. You wouldn't necessarily want to look at a full 3-month section of hair. If you could pin down the day that the event occurred, what you can do is take different segments of hair. You could fractionate out maybe 1-month sections of hair to try to better detect that single use. Or even better yet, you can fractionate single days of hair. And that's, most labs will not do that. This is really something that is still at a research level. But there are people who have been cutting hair down at less than 1 millimeter size, looking at single day exposures of hair. And each time you fractionate the hair and cut it into different pieces, each fraction is a separate test, which comes with a separate fee. So fractionating the hair can get very expensive. And if you are going to look at single day use, you really need to calibrate the hair, because you can't say exactly how fast someone's hair grows. So what I've seen in research projects is they calibrate the hair by having the person take a drug that they know they took and how much they took as a marker to say, on Tuesday, I took marker drug A, and then on the following Saturday, I took marker drug B or marker drug A. And so that is a way to see which fragment of hair matches what time period and which day. But like I said, doing something like this is still pretty much fantasy right now. It would be extremely expensive, and it's mostly just for research. But when someone develops a cheap way of doing that, that will definitely be the way to go for a lot of tests. So comparing urine tests and hair tests, if you have someone who is taking multiple urine tests to try to detect drug use, urine tests only have a window of detection of around 3 days, whereas hair detection windows can be whatever you want depending on the size of hair. And hair is continually made, so it's really like a continuous monitoring system of potential drug use, whereas urine is looking at just snapshots of time. And there is a possibility that someone knows they're going to have a urine test soon and will stop using drugs for a couple days to let it clear out of their body, and then we'll have a clean urine test, and then can continue to use drugs after that urine test. But hair doesn't allow that because it's a continuous monitor. So here, if you've got someone who's taking a drug, each of these little arrows, they stop to pass a urine test, they pass the test, no drugs found, and then keep using, the hair test is going to pick that up. So it's really good for long-term monitoring of drug use for things like probation and child custody. You can tamper with hair either by shaving the head by bleaching hair or dyeing hair. So someone's going to let their hair grow out. They know the test is going to come. Go ahead and shave their head, go to the collection site, and think, haha, they fooled you. There's no hair to test. Or they could try bleaching the hair. Some bleaching agents can damage and decrease the amount of drug that's found in the hair, and some dyes can do that as well. But usually this is focused on head hair. So the alternative is to test for body hair. So it can be any body hair. It can be underarm hair, it can be pubic hair, it can be arm hair. Usually these are not places that people are going to try to bleach or dye, though they may shave different sides of body hair as well. So let's look at finger and toenail collection. So this is done in two different ways, usually at the same time. So drug is found in the toenail or fingernail, and clippers are used to cut the tip off. It's not going to give a huge amount of material, but some. And then a scraping instrument can be used to scrape away the top layer of nail throughout the surface of it. So getting both clippings and scrapings from all fingers and all toes can eventually add up to a fair amount of material. So urine collections, we are going to save that for Dr. DeCall tomorrow. And just a quick summary on blood and hair collections. So these are observed collections. They can be confirmed and retested, so you can challenge them in court. Blood tests are going to give current use, whereas hair and nails are going to give distant use from a certain time ago. And that is all I've got. So are there any questions?
There are some questions, but first, thank you so much, Dr. Evans. That was a lot of really helpful information. And I'm looking forward to hearing the rest tomorrow. I hope people will stay online. If you want your full CLE credit, we're probably going to go until about 4 o'clock. But let me look back through the questions. The first one that came in was when you were doing the urine dip tests. Someone was asking about the cold medication that had a similar structure to methamphetamine. And they asked, do they break down to the same metabolite? And how would you know if you were getting a positive for an illegal substance versus non-illegal?
They don't necessarily break down to the same metabolite. Yeah, I don't think so. What you would have to do is take the screening test that's going to show up positive for the pseudoephedrine and then carry it over to a confirmation test. Dr. DeCall will talk about those tomorrow, but it's then the confirmation test that will say exactly what that chemical was. So those wouldn't be fooled by pseudoephedrine. It's just the screening test.
Okay. What types of drugs can be detected with a hair test?
Pretty much anything that can be detected in the blood. There may be some variations in the amount of drug that get into the hair versus blood or urine. But for the most part, you could detect the same ones in either specimen.
Okay. Then we had a couple of questions about environmental exposure. They're asking, how likely is secondhand contact to show up in hair or urine? They say this often happens with infants. Sometimes clients say that people were doing or smoking drugs around them. Is there a way to differentiate between actual use and secondhand exposure?
Yeah, that is mostly looking at metabolites. If you don't see the metabolites, then that drug was not in the body. It didn't get to the person's liver. It was just from the outside of their body, like onto their hair. So that's usually the main way to differentiate that. But you have to make sure that the lab result is not just reporting half the information, and maybe they're not reporting the metabolites, even though they should, but the metabolites were actually there. So that's when you need to go and request the litigation package from that.
Would there be a litigation package if it was a screening test?
Not really. So I've only gotten litigation packages for confirmatory tests, but some of them in some labs will include the results from the screening test as well as the confirmation test. But again, that changes from lab to lab. If you only got at the screening level, then I've never gotten a litigation package for just that. I don't know that that happens.
Okay. Can drugs be passed to a child through breastfeeding?
Yes, it's going to depend on the drug, but many of them can do that. And there you would see metabolites as well. So to try to say, was drug use just from, like it's not the same as environmental exposure. So it would look like the infant was using drugs just as well. You'd see the metabolites as well as the drugs.
Would the parent drug be passed through the breast milk or just the metabolites?
It could be both. It's probably going to be both. But so breast milk is going to have a lot of fatty material, but it also has water. So there may be some differences in drugs that, well, there could be differences in drugs that are polar and non-polar, depending on the drug and the ratios of the drug and metabolite. So if you were to measure the mother's blood, maybe the metabolite is going to be twice as high as the drug. And then if you measure the breast milk, maybe that metabolite is 5 times higher than the drug. So there can be differences like that.
Is there anything that will give a false positive on a urine test strip?
There are lots of things that can do that. I think Dr. DeCall is going to talk a little bit about that tomorrow.
Okay. Next question is, who gets the litigation package, the lawyer, or does it get sent to another lab or toxicologist?
I've only gotten them through lawyers. So I think it gets first sent to the lawyer, and then they can distribute it to any expert that they have.
That sounds right to me.
I've never asked a lab directly for a litigation package. Well, no, I'll take that back. I did. But in that case, it was a weird case. I was not working directly with the lawyer because the client felt that they did not trust the lawyer, and so they were just communicating directly with me. And in that case, since I was the one who ordered that test, I could get a litigation package without needing a lawyer. But basically, I'm the one who ordered that test. So if it was a case where Child Protective Services ran the test, then it would have to go through a lawyer because that wasn't something that the expert ordered.
Okay. dip tests produce false positives if the directions aren't strictly followed, or if there was something improper with how the tests are stored or how they were performed. Or should we leave that to Dr. DeCall?
Yeah, maybe he can answer that one. I would think not, but defer that to Dr. Paul.
Okay. And the last one on here, and we have a few more minutes if anybody else wants to add a question, is will gestational diabetes cause a false positive?
Would that be for alcohol? Is that what it's asking about, or it does not say?
It doesn't say, but maybe
You can, for something like a breathalyzer, where it is not an evidentiary breathalyzer, there is a possibility of a person with diabetes to have acetone in their blood that could trigger a positive reading on the breathalyzer. They are supposed to be designed not to do that, but your non-evidentiary breathalyzers, you can't really say for sure. It's really the evidentiary ones that the police use. They have not just a fuel cell, but they have an infrared spectrometer, which is able to differentiate alcohol or ethanol from acetone. So probably in a screening, you could get some problems with testing for alcohol just from diabetes, but not as a confirmation test.
Okay. Great. Well, that's all the questions that have been sent in, but we will be back tomorrow if you all have more questions. Tomorrow, like we've mentioned, we're going to hear from Dr. DeCall about how testing is done in a lab and hear about possible problems with those tests. And then Dr. Evans is going to be back on to talk about test reports and give us some case examples. So I think it's going to be a really interesting program tomorrow. I really appreciate you, Dr. Evans, for taking the time to present to us today. I see that you have your contact information up, and I will also send that out to everybody when I send out the materials after the program on Friday. So tomorrow we'll be back on again at 1 o'clock. You'll get out an hour earlier. We'll finish at 3 tomorrow. And then after the program tomorrow, I will send out a link where you can report how many hours you attended, and I'll process your CLE credit. And then we'll also send out the PowerPoints and any other materials that we talk about during the program, contact information for speakers, all that good stuff. So you should have in your inbox, you should have gotten it along with the first link. You should have a separate link that you'll use for tomorrow. And we look forward to seeing everyone tomorrow afternoon. Thank you so much, Dr. Evans.
Thank you.
So Dr. Evans and Dr. DeCall, if you want to hang out, if you have any questions about tomorrow, or if you had any technical issues, let me know. We can try to figure those out.